Good morning, everybody. So right now we are going to continue talking about the topics of chapter 7. When it comes to chapter 7, the last thing that we mentioned last week on Thursday was the whole idea of the classifications of the different types of reactions that we have when it comes to inorganic chemistry, okay? So far we have done number 1, number 2, and number 3. Let's actually now, as a review, proceed and classify the other reactions that we have here. So remember, when it comes to the classifications of the reactions, a combination reaction has 2 components that turn into one single product. In decomposition, we start with a product that turns into many we start with a reactant that turns into many products. In a single replacement, we're going to have an atom that is going to replace one of the atoms that were in a compound in the reactant side. And in the double replacement, we switch partners. And then in combustion, remember that as long as your molecule is reacting with oxygen, that is considered a combustion. And if your molecule that you're reacting molecular oxygen with contains carbon, hydrogen, or carbon, hydrogen, and oxygen, you will make CO2, water, and energy. So let's look at number 4. In number 4, you can see that we have KOH and H2CO3. And then now we see that the cation in the KOH is not paired with the anion of the H2CO3. The H in the H2CO3 is paired with the hydroxide. So what kind of reaction is this? Excellent job. This is a double replacement reaction. Next one. We have magnesium hydroxide reacting with phosphoric acid, making water and magnesium phosphate. So Mg is now with the phosphate. The hydrogen that was next to the phosphate is now with the hydroxide. That's where the water comes from. So what kind of reaction is this? Excellent. This is another double replacement. Number 6, magnesium bromide and potassium hydroxide turn into potassium bromide and magnesium hydroxide. Excellent. This is another double replacement. We have solid manganese reacting with copper 1 chloride, making just copper, and then manganese 2 chloride. What kind of reaction is number 7? We see the manganese. Excellent. This is a single replacement. And lastly, we have a compound that has carbon and hydrogen. We're mixing it with molecular oxygen and we're forming water and CO2. So what kind of reaction is this? That's not a single replacement. You see oxygen on both products. Think about it. Carbon and hydrogen. Thank you, Dania. This is a combustion reaction. Okay. Remember, all of your reactions are summarized in table 7.5. You need to know how to classify them. Now, one of the things is that combination reactions, single replacement reactions, decomposition reactions, and even combustion reactions can be considered oxidation reduction reactions, okay? So understand that oxidation reduction reactions are not a separate type of reaction. They are incorporated into what is happening to the atoms in these type of reactions, okay? Now, why are oxidation reduction reactions so important? So in this class, we do not go over metabolism, but if you take physiology, you will be able to look at the process of glycolysis. Give me one moment. So when it comes to oxidation reactions, in physiology, when you study the process of glycolysis, you will see how oxidation reduction reactions are so important in the body, because it's how, for us, energy is produced from food. In a practical sense, whenever you have batteries that provide electrical energy, it is done through oxidation reduction reactions, okay? To illustrate an example of a reaction, okay, that happens in one of the historic monuments that we have in this country, the Statue of Liberty. Put a 1 in the chat if you have seen the Statue of Liberty. Anybody? Ooh, some people have visited. Excellent. Okay. So the Statue of Liberty, it is actually made out of copper. Okay. And over time, that copper has undergone an oxidation reduction reaction. That copper, when it's exposed to molecular oxygen, and that molecular oxygen comes from air, has created what we see as copper 2 oxide, okay? So in this reaction, we have seen how from reactant to products, there have been changes in the different atoms that we start with, okay? So understand that in the process of oxidation reduction, whatever atom is losing electron, okay, then it's undergoing oxidation. Whatever atom is gaining electrons is undergoing reduction, okay? So if we look at the reaction here that explains that green patina that is actually at, on the Statue of Liberty, okay, we see that the copper in the reactant, okay, was solid, okay? It was not charged. It was copper at ground state. In the product, we have copper turn into a cation. We learned earlier in chapter 6 that something that becomes a cation is because it's losing electrons. And as I just illustrated, if you lose electrons, you are undergoing oxidation. So once copper loses those electrons, some atom has to grab them. And as you can see here in the reactant, we have molecular oxygen, which is technically ground state oxygen. When we look at the product, because now we have the formation of an ionic compound, we see that those 2 electrons that were lost by copper were gained by oxygen, okay? So oxygen gained electrons, it became an anion, and that's why it undergoes reduction, okay? So when it comes to the concept of oxidation reduction, it is important that we know how to calculate oxidation number, okay? And these are some general rules that we see here, okay, for calculating the oxidation number for elements or compounds, okay? So you can see these notes on the slide establishing what are the oxidation numbers, okay, for compounds. So as you can see, if you have an element by itself, it has an oxidation number of 0, okay? The elements from group 1A always have a +1 oxidation number. Group 2A always have a +2 oxidation number. Halogens usually are -1, okay? Only positive if they're paired with oxygen, because oxygen is usually -2 unless we have them in peroxide, okay? Now, you can see that hydrogen is +1 when it's paired with nonmetals. Hydrogen is -1 if it's paired with metals, okay? Fluorine is always -1. Understand that in this, we have neutral compounds. So that's why you don't see any charge in the corner. So when you sum the oxidation numbers of a neutral compound, they have to equal 0. The only instance in which we have a polyatomic ion, okay, then for polyatomic ion, the sum of the oxidation numbers has to equal the ion charge, okay? We're gonna do practice, so at least people solidify this concept of determining oxidation number, okay? So here we have an oxidation reduction reaction, okay? If we classify it based on the 5 different types of reactions that are out there, what type of reaction is this? When we look at it, is this a combination, a decomposition? What kind of reaction is this? Look at what's happening to the atoms. This is just a little more practice. What kind of reaction is this? Excellent. Yes, it is a single replacement reaction, okay? Because we see that now carbon is with oxygen and iron is by itself. Now, let's determine the oxidation number for each of the compounds that we have here. I'm going to write ON for oxidation number, okay? So out of my reactants, okay, as you can see, the first bullet point says element by itself has an oxidation number of 0. Who's going to get an oxidation of 0? The first reactant or the second reactant? Excellent, carbon. It has an oxidation of 0 because it's an element by itself. What about in the product? Who's going to get an oxidation number of 0? Excellent job. Iron gets an oxidation number of 0, okay? Put a 1 in the chat if at least that first part makes sense, why the oxidation number of carbon and iron is 0. Excellent. Now, you can see here that the first compound that we have is an ionic compound, okay? So this, you can see that it is a neutral compound because it doesn't have an overall charge. So when we add the oxidation numbers, they need to equal 0, okay? Based on the rules that we have there, this is not peroxide. So what's going to be the oxidation number of oxygen? What is the oxidation number of oxygen based on the rules? Excellent, -2. Let me just zoom in here. This is -2. But in this ionic compound, notice that I have 3 oxygens. So I need to take that into account. So I'm going to multiply that. -2 times 3. This is -6. Okay. Now, when I add the value of my cation that I have to multiply by 2, when I add it to the sum of the oxidation numbers in oxygen, it has to equal 0. So what is most likely? The oxidation number of that iron. Excellent job, +3. Because when I multiply it times 2, then I have a +6, +6 plus -6 equals 0. So understand that when it comes to oxidation numbers, and you have an ionic compound, the charge of the atom is going to be the oxidation number for the atom. So oxidation number for oxygen is -2. Oxidation number of iron is going to be +3. Okay. I understand. I had to multiply it by the subscript. I'm just assigning the atom by itself. Okay. So let me just write that note right here. For ionic compounds, the charge of the ions is their oxidation number. Okay, put a 1 in the chat if how we assign the oxidation numbers for iron 3 oxide makes sense. Put a 2 in the chat if I need to repeat that information. Excellent. So let me just show my work again. When we have an ionic compound, that is a neutral compound because it doesn't have an overall charge in the corner. Okay. When we have to assign the oxidation numbers, we know that oxygen is going to be -2. Okay. So the oxidation number of oxygen is always -2. In the context of this compound, we have to take into account that there's 3 oxygens. So when you multiply the oxidation number of oxygen times the subscript, that equals -6 value. Now, we have iron. Iron is a cation, okay? So its oxidation number has to be on the positive, okay? But how positive it is? Well, when I add it to the total value of the oxidation number of oxygen, it needs to cancel it out. So we illustrate why is it that the compound is neutral. So for that instance, we need to say iron has a +3 oxidation number. When we multiply it times the subscript of 2, that's going to be +6. +6, when you add -6, that equals 0. So the oxidation number of iron is going to be +3. But to summarize it, it is easier to say in ionic compounds, the charge of the ions is also their oxidation number. Yes, the -2 for the oxygen comes straight from the rules. Oxygen is one of those atoms that always is -2, like your halogens are always -1. And then you can see here in the rules how your halogens are -1 unless they're paired with oxygen. So because oxygen is going to be that atom that we focus on, because it's always -2 unless it is in peroxide. That's the only instance, okay? Now, carbon monoxide is a covalent compound, okay? It is also a neutral compound. And for those students that are like, how do you know, Dr. Luz, that it's a neutral compound? We don't see a charge in the corner, okay? There's no charge attached to it. So that means that when we add the oxidation number of these two values, it has to equal 0, okay? We just learned from the rules. What is going to be the oxidation number of oxygen always, unless it is in peroxide? Excellent. So -2. In here, we only have one oxygen, okay? Because it has a subscript of 1. So that means that -2 times 1, that is -2. We also have one carbon. So what is the oxidation number of carbon in the context of carbon monoxide? Because it needs to equal 0. What's going to be the oxidation number of carbon? Excellent, +2. So carbon is +2, oxygen is -2. And remember that it mainly comes from the idea that my subscript is a subscript of 1, okay? So this is what happened overall. Now, whenever we're trying to determine who got oxidized and who got reduced, I actually like to make a table, and I put all my elements that were involved in the reaction. I have iron, I have oxygen, I have carbon. And I'm going to write what is going to be, or what was the oxidation number in the reactants versus the product. For each of these. Okay, so iron went from +3 in the reactant to 0 in the product. Oxygen was a -2, and the product is a -2. Carbon was a 0, and now in the product is a +2. Okay, we need to find out who got reduced and who got oxidized. I actually like to view this as a number line, where this is 0, and these are the negative values, these are the positive values, okay? So whenever I have atoms going from somewhere negative, maybe towards 0, maybe towards positives, when they're going in this direction, you guys, these are atoms that are undergoing oxidation. When I have atoms that were positive, maybe turn into 0, maybe turn into negative. So when my values in terms of numbers are going in this direction, that means that that element is undergoing reduction. And understand that the atoms that undergo oxidation and reduction are in the reactants, okay? So when we look at the case of what happened to iron, iron was positive and it went towards 0. So let me use my highlighter tool. So for iron, it was positive and it went towards 0. So as you can see, iron got reduced, or it undergoes reduction. Carbon, on the other hand, as we can see, was at 0 and turned into positive. So that means that carbon undergoes oxidation. Okay. Now, oxygen was at -2. It remained at -2. So that means that my oxygen is what we called in these type of reaction, the spectator ion. And what an spectator ion does, as you can see, as the term says, spectator, is just looking at the atoms exchanging electrons. Like, okay, I'm just seeing what you guys are doing. I'm just here looking at the action. Okay, it's an spectator. Okay, so this is how you assign the oxidation number for the elements in a oxidation reduction reaction. Now, when this comes into words, because this is also in the homework, okay? The correct terminology is that the iron in iron 3 oxide is the one that undergoes reduction. Then the carbon in the reactant is the one that undergoes oxidation, okay? It will be incorrect to say that carbon and carbon monoxide is what's undergoing oxidation. Oxidation always happens at the level of the reactants. Who's ready to practice? Put a 1 in the chat. Excellent. So I'm going to give you guys 3 minutes. Look at the following reactions, okay? And determine what's going to be what undergoes oxidation and what undergoes reduction, okay? So I'll give you guys 3 minutes to complete this. Okay, let's get started, you guys. Let's first assign the oxidation number to the components of each of the reaction, okay? So let me just zoom in into the first one. Here we have magnesium reacting with hydrochloric acid. We're going to learn later this week why is it called hydrochloric acid, but for now, this is hydrogen monochloride. That is forming magnesium chloride and molecular hydrogen. So if you assign an oxidation number of 0 for the magnesium, you are correct. When it comes to the oxidation numbers for hydrogen and for chlorine, chlorine is going to be -1 and hydrogen is going to be +1, okay? Put a 2 in the chat if you got those oxidation numbers for the reactants. Excellent. Then let's move on to the product. In the product, we have another ionic compound, okay? So the magnesium oxidation number is going to be +2. The chlorine is going to be -1. H2, because that is an element that is diatomic, is going to have an oxidation number of 0, okay? Put a 3 in the chat if you obtain those oxidation numbers for the products. Excellent. Any questions on the assignment of oxidation numbers for the elements in this reaction?
Professor, I have a question.
Yeah, go ahead there.
For chlorine, why is it not -2? Why is it -1?
Because remember that the -2 comes from the, so the -2 comes from taking into account the subscript. I'm just assigning the oxidation number of chlorine by itself. Yes, it is -2 overall, but remember that for ionic compounds as such, understand that the charge of the ion is the oxidation number. There's a question in the chat, is the first one always positive and the second one negative? If we're talking about an ionic compound, yes. The first one is positive and the second one is negative. HCl is a covalent compound, but because we have to take into account that halogens are -1, then we tend to see that, you know, in many of them, the first element is going to have a positive oxidation number, and the second one is going to have a negative oxidation number. Other questions in terms of the oxidation number assignment? Again, I'm assigning the oxidation number per element. I'm not looking into the overall oxidation number. Excellent. So taking that into consideration, then I'm going to make my table where I'm going to put the elements in this reaction. I have magnesium, I have hydrogen, I have chlorine. I have to see what happened overall between reactants and products to these oxidation numbers. So magnesium went from 0 to +2. Hydrogen went from +1 to 0. And chlorine went from -1 to -1. So let's put in the chat, who's my spectator ion, you guys? Which element is the spectator ion? Great job, chlorine. This is my spectator ion. So when it comes to oxidation, remember, oxidation is those atoms that are going to be losing electrons. They're going to go towards more positive. So who got oxidized? Great job. Magnesium got oxidized. So that means that hydrogen got reduced. Let's go through the second example. Let's write the oxidation numbers for all the components. Let's first deal with the reactants. Cl2, that is a diatomic molecule, so that is how the element exists. So this is going to have an oxidation number of 0. Sodium has an oxidation number of +1, bromine an oxidation number of -1 because it is an ionic compound. In the product, my sodium is going to have an oxidation number of +1. My chlorine is going to have an oxidation number of -1. Br2 is in its elemental form because it is a diatomic. So its oxidation number is 0. Okay. Questions about the assignment of oxidation numbers for problem number 2? Excellent. So we're going to make our table. We have chlorine. We have sodium. We have bromine. We need to know what happened to the oxidation number in the reactants versus what happened in the products. So for chlorine, it went from 0 to -1. For sodium, it was +1. It remained +1. For bromine, it was -1, and then it became 0. Okay. So who undergoes oxidation in this case? Excellent, bromine. Who undergoes reduction? Excellent, chlorine. And in this case, our sodium is going to be our spectator ion. Questions? Determining oxidation number for elements in a reaction and determining who got oxidized and who got reduced. Excellent. Since there are no questions, now we are going on break.